Alright, so we're going to multiply both sides by dx. In multiplying both sides by dx, it cancels from this side, leaving you with y dy. And since we're multiplying the other side by dx, other side has an x, so now we'll have an x dx. That's pretty efficient because that achieves the first part of the goal here, which is get the y's on one side, the x's on the other. Once you get to that point, what you can do is you can take the antiderivative of each side. If you take the antiderivative of the left side of the equation, we're taking the antiderivative of y. So y has a power of 1. Add 1 to that power. Get y to the second. Take the reciprocal of 2, which is 1/2. Place that in the front. So there's your antiderivative of the left side of the equation. Right side of the equation. Basically same thing, right? Only we got an x. This is x to the first. So add 1, get a power of 2, reciprocal 1/2 to the front. Now, since we're taking antiderivatives, we don't have definite integrals here. We're going to have to tack on a constant to one of these sides. Usually we tack it onto the x side. At this point in the process, the equation that you have is acceptable because we're supposed to understand if I take excuse me, my derivative here implicitly, it would take me up to this point at some point. Sometimes you'll see the y side solve for a little bit more. Like we could multiply everything by 2 here, right? That would clear the fraction out of 1/2. You'd have y squared if you multiply by 2 to the left side. You'd have x squared if you multiply by 2 to the right side. Now, if you're multiplying by 2 to this constant, you could say it's twice the constant, but it's still going to be a constant that we don't know, right? So usually we don't include that factor with the constant value. We just keep that at plus c. But either of these are acceptable. That's the basic gist here of that process. All right, so on the last one we found multiplying both sides by dx made sense, right? In fact, on this one, you could go as far to say it might make sense to cross multiply. Like if I cross multiply this dy to that root y minus y, that would give me root y minus y, that quantity, multiplied to dy. And on the other diagonal here, as I cross multiply, I got a dx times a root x plus x. If I multiply those two together, the root x plus x, that quantity, times the dx. That's pretty convenient because now I've separated my y's and my x's. It's not always going to be that convenient on these problems. Sometimes there's a little extra piece you got to do at this point, but so far so good. Since the x's and the y's are separated, take your antiderivative of each side. On the left side, we've got a couple of terms here. We apply our antiderivative to. We've got y to the 1/2, so if I add 1 to the 1/2, get 3/2. Reciprocal is 2/3, so you can bump that to the front. We're subtracting y, so that's y to the first, meaning if I add 1, it's y to the second. Reciprocal 1/2 goes to the front. That equals, well, again, we got a lot of similar stuff over here, right? This is going to be a 2/3 x to the 3/2. So that's square root of x. And this is going to be plus 1/2 x squared for that x. Taking the antiderivative of each side, these are indefinite integrals, so we tack on c to the right side. Kind of like the last one, you know, this is a reasonable answer. You could clean up the fractions a little bit. Since we got denominators of 3 and 2 to play with, you might want to multiply the whole thing by 6 to clear those fractions out, make it a little cleaner. Now if I multiply by 6, here 3 goes into 6 2 times, so multiply that 2 on top, that's 4y to the 3/2. Multiply by 6 here. 2 goes into 6 3 times. Multiply that 1. Got minus 3y squared. And then we got the same kind of values on this side. So it'd be 4x to the 3 halves plus 3x squared plus c. Again, either or here on these equations. The idea being if I take the derivative implicitly and I solve for dy dx, it takes me back to something like this up here.
That would be my preference.
All right. Directions remain the same here. We've got some additional information on this problem. Got a second derivative to start with. But we got numerical values we can plug in for y and for dy dx eventually when we get to that point. And those values we got for y and dy dx that we can plug in when x is 1, the way this problem is worded. So really all that means is instead of leaving your answer with a plus c on there, it means now we can figure out what the value of c is. So that's ultimately our goal here. Okay, starting with this fun little presentation. You got the second derivative. Second derivative equals negative 3 over x to the fourth. So if we rewrite that, it's negative 3x to the negative fourth. Now if we know where we're going with this, based on the problems we've already done, at some point we're taking the antiderivative of each side, right? Now what if I take a slightly different approach here and just take the antiderivative? If you take the antiderivative of the second derivative, what do you get? You get the first derivative, right? So taking the antiderivative at this point means this side would become dy dx. And that's fine because if I take the antiderivative on the right side, well, I know I'm adding 1 to my power, so u power is negative 3. I know I'm taking that reciprocal, which is negative 1/3, multiplying to the negative 3 in front, which is awfully convenient because that gives me 1. You're taking your antiderivative now. You tack on the c. Since we know what dy dx and x equal, we could solve for c. All right, we can solve for c at this point before we proceed any further because we're not done. Right? We still have this dy dx notation, which means we're going to have to take another antiderivative. So substituting in the values that I know, dy dx is negative 1, x is 1, taking 1 raised to a power of negative 3. Don't have to get thrown off by the fact that it's a negative exponent, right? It's 1 to a power, what is it? It's 1. So c will be negative 2. All right, I'm going to take this negative 2, I'm going to plug in up here. I'm going to rewrite this. dy dx equals x to the negative 3rd. We're substituting in this negative 2 for c, so it would be minus 2. And now we're back to the other kinds of problems we started by talking about. Yep. So, need to take the antiderivative again. If we're more in line with our approach from before, we could swing the dx over. Say dy equals x to the negative 3rd minus 2, that quantity times dx. Got your x on one side, y's on the other. When you take your antiderivative at this point, now the understanding would be over here there's a 1 in front of that dy, right? So if you take the antiderivative of that 1 in terms of y, it's a constant. So you attach the variable. It'd just be y. Of course, the other way to look at that is you're taking the antiderivative of this in the first place. What's that going to be? It's going to be y. Now, on the right side, You got that x to the negative third. Add 1 to the power, get negative 2. Reciprocal, negative 1/2 goes to the front. We're subtracting 2, so we attach an x to that. Got to add on the constant since we've taken the antiderivative. Once again, we go back to the given information. We're given a value for y when x is 1. So we can substitute 1/2 in the place of y, substitute 1 in the place of x. 1/2 equals negative 1/2. 1 to the negative second minus 2 times 1 plus c. We solve for c and plug back into our step right here, we've got our answer. So solving for c, 1/2 equals, this would just be negative 1/2, right? Because 1 in the negative second is 1. This would just be minus 2. So if I do this in pieces, add the 1/2 over, that's 1, right? Add the 2 over, that's 3. C is 3. Meaning, answer would be y equals negative 1/2 x, negative second, minus 2x, plus 3.